Okay, good morning. I've got one more example I wanted to offer you guys to help you with your assignment and also your understanding of related rates problems. So here's the last one. We have a trough, a triangular trough, a receptacle for water that's 8 meters long. The end of the trough is in the shape of an isosceles triangle. And then the dimensions of the triangle are 5 meters across and 2 meters in depth. All right, we've turned on a water spigot so that the water is being poured into, so the volume's going to be increasing. The water is going to be poured into the trough at a rate of 6 cubic meters per minute. All right, so we turn the faucet on, we're letting the water run in. My question for everybody is find the rate at which the height of the water is rising when the water is 120 centimeters or 1.2 meters deep. Okay? So that's the related rates problem. So we're going to have multiple things changing over time. We're going to have multiple things changing over time. Obviously, we have water being poured into this receptacle, this container, all right? And so we have a rate at which that water is going in. And you can tell, especially from the units, cubic meters per minute, that this is going to be the rate of change of volume per unit of time. So the 6 cubic meters per minute is dV/dt. Now, as the water is going to be poured in, as the water is poured in, the level of the water, so this horizontal distance, is going to change, right? It's going to start off being very small, and over time, that's going to change. It's going to get wider and wider until right when it gets tippy-top full, the width of that water at the end is going to be almost, it's going to go right up to 5 meters, right before it starts overflowing, okay? Another value that's going to be changing over time is the height. So at any specific level, then the height of the water is going to change. Very early, it's going to be changing relatively quickly, and then a little bit later, it's going to get a little bit higher, and we're going to have to consider the height of the layers at any particular moment. Okay? And then the question should be, as the water is poured in, does the length of one of the layers change? So as it's being poured in, as it's being poured in, as it's being poured in, right from the start, right up until it gets tippy-top full, does that length ever change? Right? Does it go from 8 to 6 to 10 to 12 to 4? Does the length of the trough ever change? So we have to consider those questions. Okay? Alrighty. So we have to get started with something. What are we talking about here? We're talking about a situation where we have the volume of a geometric shape. And what's the geometric shape? I almost said it. I didn't want to. I want you guys to at least think about it. What is the name of this shape? All right? It's triangular on the end. From front to back, it stays the same. The name of that shape is called a rectangular prism. Not because the end is rectangular, but because it's the same from front to back. Of course, this is in the shape of it. The end is in the shape of a triangle, but it's the same from front to back. So in general, the volume of a prism is going to be the area of the base multiplied by how long it is. Okay, now what shape is the base? We just said it, of course. It's a triangle, and the area of a triangle is 1/2 times the base times the height. Now remember, for anything in our equation, V, B, H, L, for any part of our equation, if there's anything that doesn't change from the start to the end, then we can replace it with a number. Does the volume change? Yes. So we have to leave it as a variable. Does the base of the triangle change? All right. I don't know what happened to my picture there. Sorry, guys. There we go. Does the base of the triangle change? Yeah, it does. Remember, when we start pouring it in, relatively small, and then it gets wider and wider and wider right up until the time it's tippy top full when it's 5 meters. All right, so the base does change, so we have to keep that variable around. Does the height of one of the layers change? Again, we start off here. Does that height change over time? Of course it does, because the water gets deeper. So we have to keep that variable around. Does the length change? And that's the one that does not, right? That's the one that does not change. It remains 8, no matter if you're talking about when the water first goes into the tank, it's 8 meters long. Or when it gets right up to the tippy top, it's still 8 meters long. So the length of the trough never changes. So we can replace this fella with the numerical value. So when we do that, we could replace L with 8. Right? Now, of course, multiplying 1/2 times 8 would get me 4. Right? So right now I'm at the point where I can say the volume of this trough is going to be equal to 4 times the base times the height. Right? Should I take the derivative right now? No. If I did take the derivative right now, please don't write this down if you're putting this into your notebook, but if I were to take the derivative right now, I'd have a dv dt on the left. I would have a db dt on the right, and I'd also have a dh dt somewhere on the right. Not filling in all the blanks, but those would be the derivatives I'd have laying around. Is dv dt a problem? Nope, because that's exactly the value they gave us. No sweat. Is dh dt a problem? No, because that's exactly the question we're asking. Find the rate at which the height of the water is rising. The issue is the dB dt. We are neither told that number, nor are we being asked that value. We're not told what that number is. We're not being asked for that as a question. So that's the issue. We don't want the dB dt laying around. So I've got to back out of this a little bit. So the issue is we do not want to take the derivative right now because we'd have a dB dt on the right-hand side, and we don't want that. So what we need to do is figure out a way to manipulate this so we could replace b with something in terms of h or v. And how do we do that? Well, we use the end of the triangle. So we use the end of the triangle. Right, so here's the end of the triangular trough. It's 5 this way, and I'll move the 2 into the middle, 2 that way. And what we do, guys, is we think about the height at any time. So we just kind of pretend to stop the water there for a second. We pretend to stop the water, and we pull that off to the side. So when we stop it at just kind of any instant, what we would call the horizontal is the base, and what we'd call the vertical is the height. That's a terrible H, so I'll put it on the outside. We'd call the vertical the H. And from geometry class, we should remember that those two triangles then are going to be similar. They're going to be similar because the top of the tank and the top of the green would be parallel to each other. That makes the 3 angles equal, so the triangles would be similar. And so what you can do with similar triangles is create ratios of corresponding sides. So you can create a ratio out of the 5 and the 2 from the big end of the tank, and then I can create a triangle pairing them up correctly with the B and the H. Right? So I can compare horizontal to vertical, 5 over 2, vertical to horizontal, B over H. All right? So 5 over 2 and B over H. Horizontal to horizontal, vertical to vertical. And of course, with a proportion, we can cross multiply. So if I multiply diagonally this way, I'd have 5 times H. And if I multiply diagonally this way, we'd have B times 2. Which variable should I solve for? I want to replace B with something. So I'm going to solve for B, divide both sides by 2. So now, wherever I see a B in my volume, right there, I can then replace b with what it's equal to, which is 5/2 times h. All right? And now by multiplying, let's see, what's 4 times 5/2, guys? That would be a 10. And h times h is h squared. My equation for volume has now gotten us all the way down to v equals 10h squared. Okay? Look all right with everybody? Nice. Now is the perfect time to take the derivative, because now we'll just have a dv on the left, a dh on the right, and both of those are derivatives, rates of change, that we know something or want to know something about. Okay? So let me scooch this up a little bit. I might have to bop back and forth a little bit. I'll try shrinking that down, see if you guys can still see some of that. All right, so now let's take a derivative. I'm going to just draw a line across. So we go from the algebra geometry into the calc. So here we go. The derivative of v is 1, attach the differential. The derivative of 10h squared is 20h, attach the differential. All right, divide both sides by dt to introduce time. Then solve for the correct derivative. And let me choose my highlighter here. I don't know what color it's in, but let me choose yellow, I guess. The question over, it's written really small now, but the question is, find the rate at which the height of the water is rising. So the derivative we want to solve for is dh dt. So dh dt is then going to be equal to 1 divided by 20h times dv dt. And that would then be our rate equation. That would then be our rate equation. And we can just simply find the rate at which the water is increasing by replacing h with 1.2. Remember we said find the rate at which the water is rising when the water is 120 centimeters or 1.2 meters deep. And dv dt is the rate at which we were pumping the water in. And you might have to go back up to your original notes. It's hard to see here. But the water was going in at a rate of 6 cubic meters per minute. Okay? And so it's just a matter of punching that out. All right, so 1 divided by 20 times 1.2 times 6. And I'm not positive, I should double check that, but I think that's 0.625 meters per minute. And so the final question, it would be the height would be increasing at a rate of 0.625 meters per second. And then while you guys are still have your video on, I'm just going to double check that arithmetic just to make sure I didn't screw that up. Let's see. I may have screwed that up. Let's see, 6 divided by 20, 1.2. No, I screwed something up, guys. I got 0.25. Wonder how I screwed that up. 2. Yeah, I don't know where the 6 came from. That's a typo. Gee whiz, Mirza. When I punched out again, feel free to double check me on my math. When I punched out a second time, I got 0.25. So sorry if I typoed that son of a gun. Sorry about that. Okay, but anyway, there would be the rate at which the level of the water, the height of the water, is changing when we're at the 1.2 meter depth mark. Okay, so there's just another example. Hopefully it'll help you out as you're working on your assignment. All right, continue to work on the worksheet. I know this isn't a very long video, but just continue to work on the worksheet. Remember, you're responsible for your own stuff. Feel free to help each other out at the beginning, but then you're on your own. Okay? All right. I'll be back on Monday, obviously, and we'll continue to work on this Monday as well. So have a great weekend, and we'll see everybody on Monday.